Class number 7, sequences. Definition: a sequence. So this is a sequence. So it is Zn n equal to 1 to infinity. And we are omitting this. When we say sequence 1, we mean 1, 1, 1, 1, etc. We don't mean a set containing only 1. Okay? So by saying sequence, curly bracket Zn. So if we know that we are in the context of sequence, we drop this even. We even drop this and just put that. Okay. So a sequence of complex numbers is formed by assigning to each natural number n a complex number z sub n. So I have natural numbers, and it is a mapping from natural number to complex numbers, etc. So it's a function from each natural number, from the set of natural numbers to the set of complex numbers. The point Zn is called the nth term of the sequence. A sequence Zn is said to have a limit at z0, or we say has a limit at z0, or we say a sequence converges to z0, and we write that as limit n approaches to infinity z sub n equals to z0 if for every epsilon positive, for every given epsilon positive, there exists an integer n depending on epsilon such that the distance between z0 and zn is less than epsilon whenever the index n is bigger than this number n. So this means, so in C, suppose this is C0, and there is a sequence C1, C2, C3, etc. But the distance between Z sub n and Z0 gets close and close as n approaches to infinity. This means that every neighborhood of Z0 contains all but a finite number of terms of the sequence. This means if I look at an epsilon neighborhood, then it contains all the tails of the sequence but a finite numbers. So except finite numbers, everything else is contained in this neighborhood. All the tail of the sequence is contained in this neighborhood. 1 over n plus I over n. So if I look at this, in C, right, 1, 1, half, half, thirds, etc. So I have points here, point there, and point here, and they will get converged to the point 0. So every neighborhood around 0 contains all but except finite numbers. So there exists, so given if I fix epsilon positive, there exists n such that, so this is C1, C2, etc. After z sub n, everything else is contained in this neighborhood. If I say this is epsilon, right? So there exists n such that z sub n minus 0 is less than epsilon for all n bigger than big N. So 0 is the limit. Hence, limit n approaches to infinity of 1 over n plus I 1 over n is 0, meaning 0 plus 0I, right? B. So since we know that we're under context of sequence, this is a sequence, not a set containing minus 1 and 1. Okay. So if we draw C, there's minus 1 and there's 1. So to have a limit, to say z0 is a limit, there for every given epsilon, for every epsilon positive, I should be able to find n such that the distance between Zn and Z0 less than epsilon, for every n bigger than this number n, I should be able to find n, right? For every epsilon. So for example, if I take epsilon equals to half, then no matter, since if I say that's z sub n, then that's z sub n plus 1. Since there is a gap of 2, no matter how big I take n, after that term, every n after this term should be within epsilon distance from z0. But no matter where I pick z0, I cannot include both 1 and minus 1 in the neighborhood of half. That's not possible. No matter where I pick the no matter where I pick z0 as my limit point, I can never include both minus 1 and 1 in one neighborhood. So there exists epsilon such that there is no n where for every little n bigger than this big N, the distance from z0 to Zn for every n is less than epsilon. That is impossible. Therefore, this doesn't have a limit. So the limit does not exist. So now let's relate the limit of complex numbers to its real and imaginary parts. So theorem, let Zn be a sequence of complex numbers. Then this sequence converges to a complex number Z0 if and only if blank. If and only if its real part xn converges to x0 as n approaches to infinity, and its imaginary part limit yn as n approaches to infinity is y0 if and only if. Okay, so let's give a proof. So So since it is if and only if we're doing two directions. So suppose we assume that Zn converges to a complex number Z0, where Zn is written this way and Z0 is written that way. So we have to show this and this, right? So we have, what we have is the following. We have, when we fix an epsilon positive, there exists n such that absolute value Zn minus Z0 is less than epsilon whenever n is bigger than big N. That's what we have. So that implies, how do we do the difference of two complex numbers? That is xn minus x0 plus I times yn minus y0, absolute value less than epsilon. Well, since real part of z is less than or equal to absolute value of z and imaginary part of z less than or equal to absolute value of z. We have done this in class number 1, right? Then this means, so if you call this as w sub n, and then w sub n, w sub n, w sub n, w sub n, then this is real part and that's the imaginary part of wn. So that implies absolute xn minus x0 is less than absolute value of wn, which is cn minus c0, and that is less than epsilon. And imaginary part of wn is less than absolute value of wn, and it is less than epsilon. Oops, this is less than or equal to, and that's less than or equal to. So see what we have done. For any fixed epsilon positive, we found n such that whenever n is bigger than big N, these two are true. Hence, limit n approaches to infinity. So this is less than epsilon and that is less than epsilon, right? So that tells us that limit n approaches to infinity, xn is x0, and limit n approaches to infinity of yn is y0. Okay, so let's do the opposite direction. So what we have, now we are doing converse. What we have is limit n approaches to infinity, xn is x0, and limit n approaches to infinity, yn is y0. And we have to show limit n approaches to infinity of cn is z0. Okay, so fix any epsilon positive. Then since limit n approaches to infinity, xn is x0, this means for any epsilon positive, when epsilon positive is given, I can find n such that the distance between xn and x0 less than epsilon whenever n is bigger than n, right? And since I am able to do this for any epsilon, I can do that for epsilon over 2. for epsilon over 2, I can go further out and I can still find some n such that this is less than epsilon over 2 whenever the index is bigger than that n. So for x and y, we'll look at n corresponding to epsilon over 2. So since it is this n limit n approaches to yn is y0, there exists n such that absolute value xn minus x0 is less than epsilon over 2 and absolute value yn minus y0 is less than epsilon over 2 for n, for all little n bigger than this big N. And we will assume that n is the maximum of n for x and n for y, because n corresponding to x and n corresponding to y could be different. Right? Then, if we look at then absolute value zn minus z0, this is xn minus x0 plus I times yn minus y0. And we can think of this as z1, complex number z1, complex number z2. So we know from the triangle inequality that z1 plus z2 is less than or equal to z1, absolute value z1, absolute value z2. So by this, it is less than or equal to absolute value of xn minus x0 plus absolute value of I times yn minus y0. But this is absolute I times absolute yn minus y0. So this is 1. And by this, right? Let's call this star. And by star, the first term is less than epsilon over 2. The second term is less than epsilon over 2, which is epsilon, for all little n bigger than big N. So the proof is done. So for any fixed epsilon positive, there exists n such that for all n bigger than n, absolute value of zn minus z0 is less than epsilon. Hence, limit n approaches to infinity, zn equals to z0. So we established if and only if. 4 is a page number, don't worry about it. Above theorem can be translated in the theory of functions. Above theorem says if a complex number approaches to another complex number as n approaches to infinity, then its real part should approach the real part of the limit, and its imaginary part approaches the imaginary part of the limit. So when we translate that in the theory of functions, if f of z is written like this, and if L is this, when we say limit f of z equals to L as z approaches to z0, we say only when, if and only if, this is true when limit z approaches to z0, its real part u of xy approaches to the the real part of the limit, and the imaginary part approaches to the imaginary part of the function approaches to the imaginary part of the limit. So don't forget that we can approach z0 from every direction. So that is x comma y approaching x0, y0. If z0 is x0 plus iy0. And we can approach x0, y0 from any direction and through any curve. So for example, limit of this. So this is the real part, u of x comma y, and that's the imaginary part, v of x comma y. So to have the limit as a plus ib, we have to show limit of the real part approaches a and limit of the imaginary parts approaches b. So let's look at them separately. So z approaching 1 minus I x over x squared plus 3y. So this is same thing as saying x comma y approaching 1 comma minus 1. And this is a polynomial, and that is a polynomial. Polynomial in two variables. So what is poly over polynomial? It is a rational function. And when is a rational function continuous? It is continuous if the denominator is not 0 at that point. So we can do direct substitution. If it is continuous, it will have the limit there, right? So it is 1 over 1 squared plus 3 times minus 1. So we get minus 1/2 for the real part. And for the imaginary part, let's do a similar thing. xy approaching 1 minus 1 xy. So this is a polynomial in two variables, continuous everywhere, right? So 1 times minus 1 equal to minus 1 is the limit. Hence, the limit of this is answer. Limit exists and it is 1/2 minus I. Limit as z approaches to 0 of this. So we see that this is u of xy and that is v of xy. So limit z approaches to 0 of constant function 2 is 2. So this is fine. Now let's look at the real part. Limit z approaches to 0, x over x squared plus y squared. So here in the, so that is x comma y approaching 0, 0. So that is x and that is y, and 0 comma 0 is here. Now to have this limit exists from every direction and through any curve, it must have the same limit L to say that the limit is L. If there are two paths, let's say that's C1 and that's C2, where from C1 it is L1 and from C2 if the limit is L2, and if L1 and L2 are not the same, we say the limit does not exist, right? So suppose I approach this through the y-axis, suppose through the y-axis. So I am holding x as 0. So x equal to 0, and we are approaching y to 0. Then let me call the star. Then star becomes equals to limit. It becomes limit of one variable function, x0 over 0 plus y squared. Since y is approaching 0, we know that y is not 0. Y never equals 0. So we get 0 over non-zero, which is always 0. But you cannot say limit is 0 yet, because you have to check every other direction as well. Okay, so why don't now I'm going to approach 0 through x-axis. So let's look at the limit through x-axis. So I am holding y as 0 and x is approaching 0. Then star equals to limit x approaching 0 of x over x squared, because y is 0. Now I know that x is not 0, so I divide by 0, then I get 1 over x. And this does not exist. Right? At 0, x 1 over x graph is this. And from there and there we get plus infinity and minus infinity, so the limit does not exist. These two things are not the same, and this doesn't exist. So yeah, it is enough to say that for the real part, the limit does not exist. Hence, the limit of the whole thing does not exist. The limit of this does not exist.